Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Right, by the way. Whenever I watched Play School, it was always completely the wrong time. They were getting the kids to tell. So, 205. In the background there, I'm trying to get the version of R that's located on this machine under the desk here to load the various packages we need for random effects models, which is the topic of later on today. But before we do that, we'll finish off yesterday's stuff on two-way analysis of variance. So your homework was to tell me what the constraints are going to be. What constraints do I have to specify to sort of tell another statistician that I've used some coding here? So I've got to specify constraints for both of the age factor and the gender factor, and I probably have to specify constraints on the age-gender interaction as well. What constraints are applied if I've used some coding? So we've used some coding. If I'd done it manually, as per the brick, I would have basically set up 0, 1 indicator variables. But actually what the brick did was it set up 0, 1 indicator variables. So in fact the brick used treatment coding, but I used some coding when I did the code yesterday because I sort of said contrasts equals list, and then listed both the factors and basically sort of said equals some contrasts. Well, the first thing is that all the alpha i's summed over I have to add to 0. Okay, so there's 3 age groups. It's going to fit 2 of the age factors, and I can find the third by subtraction from 0. So I add the 2 it does fit together, take the negative of them, and that's the third one. In other words, I'm saying that alpha 1 plus alpha 2 plus alpha 3 equals 0, and alpha 3 by default will be the one that's not fitted by R, because R's default when dealing with some coded factors is to fit the first 2, not fit the third. The third becomes the reference category, and you can get the parameter for the third by basically undoing your sum contrast. Some constraint. Okay, so that's age. For gender, it's fairly obvious, but there's only 2 levels this time. So that's enough to specify the constraint. That's just basically what that's just useful stuff to know. Okay, so in that sort of sense, a lot of you don't need to, unless you're specifically asked, tell me how many replications. So in this sort of sense, we've got just note here that that's the number of replications here. And those are the treatments. 6 age by gender. All this is embellishing the description. useful stuff, but in fact, any good statistician could work out what the hell's going on from a lot more minimal description here. So there's six age by gender treatments with 6 replications of each for a total of 36 observations. Okay, so what's the last sort of constraints I have to include? Is this also constrained? Yes. It's constrained both ways. It's constrained in the row dimension. And in the column dimension. What do I mean by that? Well, let's think about the setup here. We've got gender. One equals female, 2 equals male. We've got age. 1 equals elderly. 2 equals middle. And 3 equals young. And we basically have a 3x2 grid of our treatments. And we're going to have an interaction term there, and the negative is going to be there because they have to add up to 0. Because we have to add up across the common dimension. And here, well, this one will be the negative of the sum of those two. So that those 3 add that way down to 0. And not surprisingly, the negative of that is this. So that adds to 0 and that adds to 0, and the whole thing adds to 0 there. It's constrained every which way but loose. So how many parameters will I actually get here? Well, I'll get given that one, and I can work out the other 4 by subtraction from 0 in one direction or the other, can't I? So it's only going to take 2 degrees of freedom to fit the interaction term, but I'm actually fitting really, in effect, 6 parameters, 1 for each of the age by sex cells. And notice all of this came from the knowledge that the R default for some contrasts I can't spell contrasts. Is to use the last category in alphabetical order. It's actually, strictly speaking, like I said yesterday, alphanumeric order as the reference category. The reference category is the one we don't fit, and the one we work out by subtraction from the others. If you wanted to set up a different reference category, what do you have to do? Actually, the simplest thing in R is to basically change the name of your levels so that they're alphabetically the way you want them to be. You know, just give them just add a thing on the front that sort of gives them the right alphabetical coding. Alternatively, you can set up your own 0, 1, -1 indicator variables, and therefore you can fix the reference category and you can work out which one doesn't get fitted. let's just for an instance compare that with treatment contrasts. See if I use treatment contrasts, how would I specify this? That's if I'm using a 0, 1, or what's typically called dummy indicator variable coding. Our default is the first category in alphabetic order. So notice that's actually alphanumeric for those computer science people who know the difference. And so it's going to be, the treatment contrast would be that alpha 1 be alpha 1 would be 0, tau 1 would be 0, and that's basically the alpha for elderly. This is the tau for female. And here's my gender times age setup. I'm going to set that one to 0, that one to 0, that one to 0, that one to 0, and I'll basically fit these two. So that in each row and column, the first one is 0, and again, constrained all the way around. I still only need 2 degrees of freedom to fit them all, to fit the entire term, and it's always easy to interpret this one, because basically you just got to pick out the bits you need. This one, the sum coding, you've got to do a little bit of work. You've got to basically... So let's just go quickly to yesterday's example and have a look at the work you have to do. Okay, that's finished running, so hopefully we'll work again properly next time. So, just out of interest, how do I know that contrast.sum for a 2-level variable? How does it do the coding? Well, it sets up an indicator variable that is 1 if you're in the first group, 0, well, -1 if you're in the reference group, which is the last group, and 0 otherwise. There's the law of excluded middle here. There is no middle category for there to be a 0, but we don't fit the second one. Similarly, if I do contrast.sum for 3, I get the one not fitted is the third one, the last one. For the first one, it's a 1 if we're in that category, -1 from the reference category, 0 otherwise, and so on. That's the coding used in the background. And the second one's also coded up. Sum for, let's attach the trade and data first. Remember myself what the names are. So, if you like, there's the actual matrix that's going to be fitted for the gender one, and you can sort of see where it's got 1s and 0s and -1s. Okay, 36 observations, so there's, well, it's actually omitted 8 rows even. It's a large matrix. Okay. So when I actually did do this sort of stuff, let's have a look at the summary. And compare that with the cell means, the age means, and the gender means, which all should be stored away because I'm using the same workspace as I used the other day, and the overall mean. So, the overall mean, because it's a balanced design, is equal to the intercept. Hence why I used mu as my intercept in the model specification. Here's the age 1, the age 2. If I want age 3, I've got to add those together and take the negative of it. And I can use that to get from this, from here to these means. So that minus that equals that. That plus that equals that, and that plus the negative of those two added up equals that. Make sense? To get to the gender one, I can go from that plus that gives me the females, that minus that which is negative, so adding on 0.389 gets me to there. And similarly, I can get from any of those by adding on a little extra to get myself to the particular cell mean, if I did a interaction term. But actually I haven't done the interaction term, I've given you the one with the so here's the one with interaction. And yes, I can get from those to the cell means by adding enough of those in the right way. All make sense? Okay. So that's how it's modelled in the background, and it means that what we've got here can be used to answer certain questions. When I look at these parameters, I can see which of the age groups differ from the overall average, and it seems that both of them do. Okay, so what's happened with the overall average? Remember the mean plots? Okay, so there's the age group comparison. So what's happened is the overall average has ended up somewhere in the middle here. And yes, basically everything differs from the overall average because both of these two are significantly below it, and that one's significantly above it. And that shows in the parameter estimates for these models. Okay. Even though there's an apparent interaction here, suggesting that elderly people get a really bad deal if they're female and a better deal if they're male, it doesn't actually differ compared to the overall thing. It might as well be a flat line, even though it looks like there's a crossover point there. In other words, given this many replications, if there is such an effect, we can't detect it. It's not significant. So that's the age-gender interaction. So typically interactions show up as some sort of crossing on the plot. Or in this one, the fact you're seeing something different going on for one of the groups compared to the general pattern would suggest that that's also suggestive of an interaction term. But the bottom line is interaction terms don't seem significant. But I could have told you that from just doing this alone, which tells me that the place to look is not in the gender comparisons or the age and gender combinations. The place to look is in the different age groups.
So previous graph there was a crossover, but it wasn't significant. So would you perhaps go back to the diagram and see if there was like a significant error in the indicator or something?
Well, I mean,
There must be something there for it to.
well, it's indicative, but it's not significant. Is the point? I mean, so we don't. Again, we've got a lack of evidence here. Okay, it could be that little old ladies really are getting stiffed on the trade-in price, but no, we don't have enough evidence in the context of this experiment to say that conclusively. Again, if you really think that's likely to happen, then you design a different experiment where you really, you've got a little old lady group versus the rest, sort of thing. And this is why the BRIC concentrates on basically doing the confidence intervals for the 3 age groups. Because what you're getting here is you're getting a pretty good indication of what's happening as the stories in the age groups. And so those 3 confidence intervals that they generated there, oh, that's marvellous, isn't it? So what you're getting there is you're getting a pretty strong indication that, so I'll run this bit of code again that has calculated those, this overcomplicated bit of code here that basically calculated all the confidence intervals for the 3 age groups without any labels. And you're getting a pretty obvious 3 non-overlapping confidence intervals. Well, the elderly and the young overlap, but the middle one doesn't. In other words, that's because that's where the story lies here. Okay, any more questions on that before we move on to something else? Okay, actually, because we don't have any real write-up of this in the BRIC, it was always the additional topic for the graduate students. This bit, the idea of adding in random effects. I'm going to work my way through Bronwyn's slides for this. I have modified them a bit. And if you want to read up any more about these things, then Chapter 8 or 10 in the far away, depending on which edition you've got your access to. I suspect by now there's quite a few copies of the older edition available if you want to buy a hard copy. I think you can certainly get one or both of those as e-books from the ANU library. And Chapter 5.6 in the statistical sleuth, which is also referenced in that references you've got. So anywhere there will give you sort of a reasonable rundown on these things. A fixed effect we think of as an unknown constant we're trying to estimate from the data. A random effect's a random variable, and we typically want to estimate some sort of parameters associated with that random variable. Now, because it's a variable, it's got a variance parameter is typically the key parameter we want to estimate. And this is most powerful when we've got something like a grouped data structure. If you think about the idea of, say, studying school children naturally cluster into classes within age groups within schools. Okay, at each of those different levels, there could be a different random effect happening. Okay, there are obviously differences between individual children within a class There are differences between variability between different classes in the same age group. Definitely variability between the age groups, because children learn at different rates. They get to different learning stages at different age groups. And there's definitely going to be variability between schools. And all of those things can be seen as being random effects that are happening in the background. They're sources of known but unwanted random variation in your data. And typically, you've also got, if you've got a set of unit observations seen as a random sample from a larger population, you can think of there is definitely random variation going on depending on which sample you choose. So let's have a look at an example here. It seems to be a thought example, but we actually got some data to go with this. The manager industrial plant wanted to determine whether workers with the same skill level. So let's say we've got a whole bunch of workers who we've trained up. We give them a certain amount of basic training before we let them loose on the machines. In that sort of sense, they've definitely got at least a comparable skill level. They've probably got different experience levels and other things we probably should measure, because they're sources of variability in the process. And we want to see if basically all of our trained workers, is there differences between our trained workers and the number of units of some automobile part that they're manufacturing. Some workers can manufacture more of these parts consistently than other workers. 5 workers were randomly selected. So this is the second example, the example of where samples taken from a larger population. And we know there's random variation between individual workers. Okay, so a couple of ways of expressing the model. We can think about the observations within worker being independent with some sort of known variance. We can also think about them as being some variance between workers. Okay. If you like on expectation, we'll have some overall mean, but we'll also have to consider a worker mean. We could reparameterize that model and think about it a slightly different way. Essentially by basically sort of saying, well, okay, we can think about it for some sort of mean effect plus some worker effect. Okay, so the difference there, the first one is actually what's called the random effects model. This is actually the sort of one-way analysis of variance model that we fitted. We're basically sort of saying there's a fixed effect associated with the workers. I don't like the labelling on Bowman's slides. I probably should have put a bit more in there. Okay. So what we're saying here, though, is that there's 2 variance components going on here. The variability between workers is a unknown, but unwanted variability in our main comparison. But actually here our main comparison is the workers, so it's not actually the best example for this. We'll see more complicated examples next Monday when I sort of generalize this to sort of fit it into more general experimental designs. But yes, we've got a variation in worker productivity and variation in the measurements, the number of units produced. So what we've got under this is some underlying covariance structure. There is some, if two units are produced by the same worker, they are related. They're not independent of each other anymore. So we'd like to separate out that variance in a lot of situations so we can consider just this variance, which is, if you like, typically the variable we're interested in, the number of units produced. But really, sometimes we might be interested in what's going on between the workers as well. Now, typically, we can look at these 2 variance components as being, if there's a real difference between workers in their productivity, this is large compared to the overall variability that's going on. It's something we would have to account for before we could actually make a comparison of the number of units produced by different processes, say. So this typically is a sort of calculation we're going to do quite often. We're going to look at how much is the random effect as a proportion of the overall variance that's going on. And that's called the intraclass correlation coefficient. Really highfalutin term for basically sort of saying how important is this source of variance in the overall scheme of things. Worker here is a classic example of what's called a blocking variable. Blocking variables are typically variables that we know there are differences between them. If we do agricultural experiments, and this is where the term came from, we have our experiments arranged in plots within blocks. But, okay, due to physical constraints, the different blocks may be different warehouses, which receive different amounts of, different glass houses, which receive different amount of sun, and so on. You know, one might be under the shade of some trees, one might be, you know, sort of out in the bright sunshine. We know there's variation between the glass houses. So if you like the blocking variable there's variation between blocks that we'd have to know or account for in order to analyse the results of our experiment. Workers are a classic example of that. We know that it's typically going to be random variation between different people working. Some of these things we can probably measure and account for, like, say, the years of experience of each of the workers. How practiced is this worker? We could actually include that in our model as a covariate. Okay, that's next Monday's topic. Analysis of covariance. But some of it is just going to be random variation between workers. And we'd like to remove that source of variation if really what we're interested in is you know, what's going on with the production or the yield in our experiment. So here's the fixed effects model. And they don't look that much different. Really, we're going to come up with a treatment and an error sum of squares. If you like, the expected mean square for our treatments is going to have both the overall variation plus some additional stuff due to the difference between the different treatments. In this case, the different workers. Okay, and they're not that different in appearance at the moment. So let's have a think about how we would test for a significant worker effect under both sort of models. So let's roll out some R. Okay, so here's the observations for the first worker, second worker, third worker, fourth worker, and fifth worker. Number of units produced in a fixed period of time. So most of the things we've tried to control and make the same by sort of saying, okay, we measure their production over a set period of time, presumably the same time of day or same sort of point of the production process for everybody. Control the things we can. We know there's going to be some variation between workers. So we're going to add all those observations together. And we also have to have some sort of indicator for which worker we're going to have. So let's... So overall N is 30. We've got 5 different workers. It's 5 different workers and 6 observations for each worker. So here's our data. So notice we've set work up as a factor variable, even though, because we've forced it to be a factor, R will correctly interpret it as a factor variable whenever it fits it. And it notices, even when we ask for just to print it out, it notices it's got levels. So it's been defined as a factor variable. If it wasn't, because it's numerically coded, we probably would have to sort of put as factor when we fitted it into a model. So, the overall variability in the process, here's the mean of y. Here's a null model. What's a null model do? Well, it just sort of says the best we can do to model things is look at the overall mean and random variations away from that. Okay? What's the plot of a null model look like? It's a single column of data. 30 observations centered around some mean, that will be the overall mean, with random variation around it. The normality assumption doesn't seem to be too bad. And again, I'm not going to try bother inserting that plot. Here's the analysis of variance table. What is the analysis of variance table here? Well, it's really just, it's a collapsed analysis of variance table. That's really the total line. It's an estimate of how much random variability we've got here. We've got 30 observations, so we have 29 degrees of freedom overall, and that's basically the variance of y. It's all over here because there's nothing to explain what's going on. And similarly, that's a pretty degenerate one as well. So let's first of all put in the whole thing as a sum-coded. We'll explain why by workers. Because we're using AOV, this is treating things as a fixed effect. It's assuming that worker is a known and fixed effect. It's not a great assumption, really, is it? Because it's sort of the workers really are going to vary from worker to worker. When we set up our previous experimental designs, when we set up the different fertilizer treatments, we carefully controlled how much fertilizer went into it. So the X was the factor known fixed variable. Our assumption that the X's are measured without error is good. Here, we're actually not. If we do this, we are assuming that the worker is measured without error. In other words, we're not really accounting for any separate variation between workers. Well, we are, because when we do the analysis of variance, we'll see what happens. Here's the plot. Oh, I haven't run the model yet. It helps if I do that. Okay. Not surprisingly, we see 1, 2, 3, 4, 5. 5 columns of data with 6 observations in each column. Some of them are overlaid, so there might only be 5 observations there. Actually, no, we don't seem to have any double-ups. We seem to have 6 in each. We've got different variability within each worker. Probably not too much different variability. And we've certainly got a difference in the number of units they've managed to produce. I don't know if this one's either a slacker or relatively inexperienced, because we haven't measured those criteria to actually include them in the model, have we? And here's the summary. Oh, sorry. No, it's not. Let's just go through the other plots first. Here's the summary. Another summary, really, if you think about it, it does take out a variance component for the workers, which is if you like, the fixed effects approach does actually really account for variability between workers, variability between groups in this case. So even though it's not really the right assumption, it's probably going to give us a model that gives us pretty much the same results as making the right assumptions. And when you do that, basically because we use some contrasts, we get an estimate of, there's the overall mean, there's how much worker 1 was below it, how much worker 2 was above it, how much worker 3 was below it, that looks like the slacker. There's worker 4, and we can also work out worker 5 by adding those 4 together and subtracting off 0. And again, because it's a nice balanced design, everybody did the same number, it will have the same standard error. I can also compute a t-statistic for that as well. I can work out which ones differ from the overall mean. This is telling me there's a difference between workers, and that's basically telling me where those differences lie. Okay, let's redo this as a random effects model. The syntax here is a little confusing at first. What we're going to say is y is going to be modelled by an intercept model, but it's going to be a different intercept for each of the different workers. So it's worker within intercept, if you like. So it's really refitting that null model, but allowing for some random variability between workers. Sorry, I need to add my libraries in first. Hopefully this is still going to work. It's giving me some warning error messages, but let's try.
The first line, MMOD. Just not. One more R. It's called one more R, additional R.
Yeah, that's the unit effects model with random effects. It's the name of the thing, but it's actually in this package here. So the trouble is when I loaded this, it's not loading it correctly. So if I go install. Yeah, the trouble is this is going to take a couple of minutes. I was hoping that I'd basically managed to set it up for R on the machine by doing it but I didn't. I did in the other example. Sorry?
Yeah, updating the hours number because like it's 3.5.1 now. It used to be at 3.5.
Yeah, I know. This is all. Using these things. The sensible thing to do when you're working with R is to download the latest version and update all your associated packages, and do that on a fairly regular basis. Because otherwise you've got different bits of R trying to talk to different bits of R, and because they're already reasonably incompatible with each other because they're already written by a whole bunch of different people. This is the disadvantage of freeware.
So why don't we just use LNG?
That's what I will do next time. Okay, it's just that I'm actually, this is because I'm using Bronwyn's slides, and I wanted to basically show exactly what she got there's a corresponding, the stuff that shows in the slides corresponds to what's shown in the output here. Okay, and I just wanted to keep those consistent without having to update them too much. Trouble was that she wrote those slides back in 2014. So your point about the fact that there's different versions of R going on here is pretty well right. Let's try it now. You see, again, you get the warning message that we're working with different things here. Okay, this time it's worked. Here's the plots. Don't look much different from the plots we saw earlier. What has changed? Oh, sorry, that's because I'm still running the fixed effects model. They don't look different because they're exactly the same. Okay, so what do I get this time? Well, first of all, I don't get it. Do I get it? Has she tried to plot this? This is the trouble about using Bronwyn stuff. She's never actually going to be totally consistent. Not in the sort of painstaking way that a sort of a pedant like I am. Okay, so what we're getting here is we're getting a linear mixed model fit by Remmel. That's restricted maximum likelihood. It's an approximate method. Okay, it does require a sort of iterative approach, but as we'll see later, we start fitting our GLMs with iteratively rated least squares. It means that what's happening in the background is it's basically fitting a first attempt at the model, refining it, running through another iteration and keeping doing that until essentially we get to the stage where the model doesn't change. And essentially that's it's reached the sort of the point where it doesn't change that much. That's where the Remmel criteria is set. It says it's now converged. We now have, if you like, sort of stable estimates from this model. Okay, we're getting some sort of variance component for the workers, and we're getting some leftover variance. So what we're doing is we've done two separate estimates of variance. The variance due to the differences between the random workers, if you like, the workers who are showing random variability from worker to worker, and we've got variance within workers, if you like, and they should be quite similar to some of the things we found earlier. In fact, if you work through Bronwyn's slide, you can derive one from the other. In fact, if I go back to this, you find that you can basically, if you take that minus the residual variation, divide by the number of workers, you can actually get the estimate of the variance component for the workers. So a little bit of maths shown on one of Bronwyn's slides. So this is a balanced design. In other words, the answers we need we could have got from either version. We could have got it from the Remmel model, or we could have got it from the fixed effects model. In other words, because the fixed effects model is allowing for some variation between workers and using decomposing that in the analysis of variance table, it's really done the same job. For non-hierarchical models where we don't have different random effects happening at different levels, essentially that's always going to be the case. So these simple models, we could model these things as a fixed effect and it wouldn't have much difference. This stuff comes into its own when we've got different effects going on at different stages. So when I was talking about that hierarchical model, children within classes, within age groups, within years, within schools, and I've got different random effects at each one, then I probably would need to set up explicit random effects models for each of the different random effects. Notice that the likelihood ratio test is what you'd use if you had an unbalanced model, because it's a little bit more robust, but in fact, as long as it wasn't too unbalanced, you'd probably get pretty similar results from a fixed effects or a random effects model still. I won't go into that one because I'm not sure I'm going to come back to it again. Notice there are some differences. Here's the various bits you can get out of, because I haven't managed to load the ARM model yet, I haven't got the standard error fixed effects for that. You can compare, get all those things working for yourself and do the comparisons, and you'll notice there are some differences between the effects that are measured, estimated by Remmel and those estimated by the basic least squares in the fixed effects model. The differences are we are modelling things under a slightly different parameterization, but even accounting for that, Remmel is an approximate method, and it's giving you slightly different estimates in this sort of situation. Okay, so because it converges to something that's a little bit off centre, if you like. The nice thing about Remmel is it does work pretty well in estimating some very complicated effects, and so the fact that it doesn't give us exactly the same estimates as you get in a nice known mathematically well described thing like least squares is not too much of a worry. Okay, so that's a simple random example of a random effect. I'll show you how that fits in with everything else we've been doing on Monday. Okay, and then we'll also look at the